So hopefully you've pulled up the script that we've been working on so far, and we have gotten through quite a bit of stuff. I'm just going to clear out my windows so that we're kind of starting from scratch. So what we did first is we made sure we were in the right directory. We loaded the libraries that we need to do the things that we need to do. I had asked you to install this new library, Agricola, because we'll actually use that a little bit today. You read in your data file, you have a number of different ways in which you can go about finding if the data file was read incorrectly. You can actually just get the first 6 lines of it. You can look at the structure of it. One of the things that structure tells you, and you might have had this problem when you were dealing with the MITE data that I assigned to you for homework for today, for practice really. Because the hosts in the data set that's in the PowerPoint were given by numbers, when you then go to do something like an ANOVA or a Levene's test or something like that, it doesn't do it, and it's because anytime R sees numbers, it assumes that those numbers are intended to be numbers, and so you have to convert those numbers to a factor using as.factor. So if you had designated your column host in a data frame dat, you would use the assignment operator, and then you would just type in as.factor $host. And when you do that, it basically tells you whatever is in the host column, treat that as a factor rather than as an integer, which is what it was probably treating it as. And so that's something that you always have to look at. One of the reasons I like structure, the structure command rather than the head command for looking at your data, is that it tells you what type of data you have. Character, integer, number. And so that's actually more useful than just seeing the contents of your data file. It actually tells you not only kind of what the contents are, but it also tells you how R is viewing those contents, and that's useful to know sometimes, especially when you try and do something and then R won't let you do it. So actually right now it's treating treatment as a character, but it's not treating treatment as a factor. So I'm going to just tell it to treat treatment as a factor. And now if we go back up and do structure again, it shows that as a factor with 5 levels. And that's actually more useful because we can then see what the levels are. And you can see that R has reordered them in alphanumeric order. Well, I don't want R to reorder them, so this little thing here basically keeps the order the same so that they're in the same order that they appear in the data file, because I've put them in the data file in that order for a reason. We talked about getting residuals, running a Shapiro-Wilk test, running a Levene's test. Demonstrated that the Levene's test is the same as running a ANOVA on the deviations. You can get summary SE. You can look at kind of what the differences are. 10 observations, these are the means. Looks like the control is growing fastest. We've been all through this before. So we did this transformation. We tested it again because there was a significant Levene's test, and now the Levene's test is not significant, although just marginally so. So then we ran the analysis. And so the first thing that I want to do is just go through and give you a couple of ideas here. You see that every time we do something, we're having to type out the response variable, the categorical variable. We have to always give it the data, et cetera, et cetera. We do that for Levene's test. We do that when we calculate the residuals, et cetera, et cetera. So one of the things that you could do up here at the top of your script, whenever you start dealing with this, is you could actually just here at the beginning, you could specify the model that you are working with. And when I use the term model in statistics, a model is just your way of thinking about how things operate. So the model in this case is that growth of these pea plants is explained by treatment. or a better way of saying this is that variation in the variable growth is explained by the data being divided up into different treatment. And so you can think of this tilde as the is explained. So treatment is explaining variation in growth is one way of thinking about that. If you then say, oh, so this is the model for data equals that, you could use the assignment operator to assign this to model. Then, whenever you want to do something like get the residuals for that model, rather than type all of this out, you can just do this. When you want Levine's test for that model, you just put model in there because you have assigned your statistical model to a shorthand tag, an object. And then when you go to do your analysis of variance, rather than AOV, that stuff over there, you're just taking analysis of variance for this model. And you can also then shorthand that. So if you ever want to look at that again, you don't have to type AOV model. You just type analysis and it spits that out for you. So that's one shorthanding way. I normally do this in my own scripts. I'm not doing this, haven't been doing this with you guys yet because I want you to get familiar with the syntax, but I think you're finally getting familiar with the syntax of how R specifies models. And so I think you can start building in some shortcut systems for yourself. Now, if you ever get 300 lines into a script and you forget what exactly the model is, all you have to do is type in model and it will give you what that model is. It'll just give you this text, essentially. And then you can remind yourself, oh yeah, this is the model that I'm working with. I still think that I'm still doing the thing that I thought that I was doing. So just saving yourself some keystrokes using the assignment operator. Jens, do you have a question? Nope. Okay. All right. So we could, for example, actually let's specify the model above residuals. So if I type in no, not treatment. For this one, it would have been growth tilde treatment, comma, data equals that. So here's a thing that we have to do. We have to actually assign a model to it. So we would have to put AOV out in front of this. This is one of the least helpful of all of the error codes. Oh, I see what I did. Let's go back, try this. It helps if one knows how to type. Okay, there it goes. So it actually has to have something in front of it. It can't just be text. So when we type in model, um, it actually runs that thing. So actually, you have to make your model the actual statistical model that you're dealing with. So you would have to have AOV or linear models or whatever it is that you're dealing with. In which case, you would just put, if you want the residuals, you would just put model in here. So the next line that we have is actually getting the residuals for that thing. So in theory, if we go in and just replace everything that is inside of here with the term model, it will give us the residuals that we had before. And then we can do a Shapiro-Wilk test on those, and it gives you the same Shapiro-Wilk test value that we had before. So just shortcutting, saving yourself some typing. In my experience, the less typing you do, the less possibility you have of making mistakes. And so less time spent debugging the script that you've written, etc. So there's that. In a similar way, so I built my own graphing block to graph these data. I've called my graph p-growth. It's got a lot more stuff in it because I'm doing things like labeling the x-axis and the y-axis. I'm giving the whole plot a title, etc., etc. This is something that I went through last time. So mine looks a lot neater and tidier than yours does probably because I've gone through and I've set what I want the x-axis labels to look like. I've given the x and y-axis titles. I've given the whole plot a title. And then I've also set what the thematic elements are. So I'm doing things like controlling the font size of the text in all of these places. And the reason that I'm doing this is that ultimately I want to put this out into a report so I can go here on my in my graphing pane here. I can go to export. I can save this as a PDF. I can save it to a particular size, standard proportion. Save it as something. And then when I save this as a PDF, this PDF looks kind of normalish rather than looking weirdly proportioned and has text that's too small, etc., etc. So that when I produce something, I have a figure that actually looks nice in the end rather than one that doesn't look nice. And one of the things I might want to do after I see this thing blown up is, for example, I might want to increase the font size of the x-axis elements. And so I can do that by just basically going in here and take axis, text, x element, and increase this from 14 to 16 if I want. And then just rerun it. And then output it again. So it looks all squinched up in here, but when I get it out into the world, these are now a little bit easier to read because I've increased the font a little bit. You can increase the font however much you want it to increase the font. So ultimately, this is what you're trying to work on, is getting something that looks presentable if you're going to put this in a report to someone. As a result, once you have a set of graphing elements that you are happy with, for example, this theme block, this is something I went through. Did I go through this last time or 2 times ago? Was it last time? So you can take this thing, you can just copy it out and put it in its own little shorthand assignment operator, run that thing, and then, whoops, when you run that thing, if you then go and just type in th, it just gives you all of that graphing block. This is all the specifications that you have in that graphing block. And so now, rather than whenever you make a graphing block, having to retype all of this in or go someplace and copy and paste it, you just type it in there. Let me clear out this figure so there aren't any figures in there. All I've done is I've replaced all of that text with a TH. When you run that graphing block again, it gives you a graph that looks like the graph that you had before. So once again, saves you two things. Saves you having to retype all that stuff or go and find it and then copy and paste it. The other thing that it does for you is that then every graph that you have that is associated with this analysis will look exactly the same in terms of its style. And that type of uniformity, it's a small niggling thing, but especially when you're writing a paper for publication, having graphs that change style from one graph to another, editors are going to throw that stuff out. They're going to say, go back and redo your graphs and make them uniform. And so finding ways of automating the uniformity of the output that you're producing is always a good thing. Once again, if you're doing this for the real world rather than just doing this for a class assignment. So get in these habits now, and they'll pay dividends for you later in extra work, which should be working smarter, not more or harder. Okay, so those are just some things that kind of are carrying over from the last couple of days. I asked you guys to figure out how to run a Tukey on a significant difference test within R. Somebody give me the syntax for that. Capital what? Good. What packages is this in? Do you know? Okay, multi-compute. So that's actually now been folded into RMISC. Oh, no, sorry. It's been folded into CAR, I think. So I think you just need CAR for this. Chance, do you have something different? Okay. So what's the syntax then? So this is how you call it up. What are your arguments for this? For me, that's dat. Hmm? Oh, so you actually are doing it a different way than I do it. Yeah, let me see what you've done. Oh yeah, you were doing it a different way. CONF level, is that right? And that's it? Okay. So what I'm going to do is I'm going to do what you just told me to do. Is that the right syntax that I just put on the board? Oh, I'm going to get an error. Why am I getting an error? So there's no applicable method for Tukey HSD. And the reason for this is that I have not added this package. So what's the package? Okay, hold on again. What is it? MULT? Multcomp? Capital what? D. B, is it B? Oh, violin, V. Ah, masks. Dot V?
Yeah, not dot V, just capital D, table.
Capital V, IEU.
Is that what you put that
Going to do this way. Oh no. So what package did you guys use? What's that, Logan? Okay, all right. So I think what this probably is, let's do this. Okay, so this X, all right, so here's the deal. The default is 0.95, so it's a 95% confidence interval is the default, so you don't actually have to put that in there. X is actually the model that you're using. So you could do this a couple of ways. You could do this treatment, you could do this transdat tilde treatment data equals dat. So you could do it that way. Nope, you couldn't do it that way. Actually, I have to give it the fact that it's an analysis of variance. Oh, I don't know what my issue is. It's based on an analysis, so let's do this. Okay, there it goes. So Logan, what do you have as your argument? The first thing in your argument in your set. Data nova. What is data nova in your? Oh, that's your actual analysis. Okay, that's your analysis. Okay. So for this, it isn't the data frame that you put in here. It's actually the whatever your analysis is. So if you did AOV transdat tilde treatment data equals dat, that goes in there. You can put confidence. You can put in what the confidence level is, but the default is 0.95. So the only reason you need to do that is if your confidence interval is going to be something like a 90% or a 99%. You want to test those differences at a different alpha level. You would change that alpha level there. But otherwise, you don't really need that at all if you're going to be testing at an alpha level of 0.05. So what you have here then is all possible combinations. This is what the two keys on a significant difference test does. So it tells you here, two key multiple comparisons of means. The family-wise confidence level is a 95%, which is basically saying that's a 0.05 alpha level. Here is the model that you're testing. And then it basically says, well, what's the difference between control and 2% glucose? Well, that's significant because the p-value is less than 0.05. Is control different from 2% fructose? Yes, it is. Is control different from the one-to-one mixture? Yes, it is. Is control different from sucrose? It is also. Is fructose different from glucose? No. Is the 1-to-1 mixture different from 2% glucose? No. Is 2% sucrose different from 2% glucose? Yes. Is the 1-to-1 versus 2% fructose different? No. Is sucrose different from fructose? Yes. Is sucrose different from the 1-to-1? Yes. And so what it's basically telling us is all these differences that we saw before. Control is different from everybody else, and sucrose is different from all of these and the control, and these three are not different from one another. All of that is what you're seeing in these p-values. So if the p-value is less than 0.05, it's significantly different. If it's greater than 0.05, it's not different. And so whenever you look at this table of all pairwise comparisons, it should conform to kind of what you get out of the figure. This is different from everybody else. So control, 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 control. Is control different from that, and that? They are. Is sucrose different from these three? Sucrose versus control is different, obviously. Sucrose, glucose, different. Sucrose to fructose, different. Sucrose to the 1-to-1 is different. And then these comparisons, which are single sugar to single sugar, not different. Single sugar to single sugar, not different. Single sugar to single sugar, not different. So the Tukey analysis should reflect what you see in the graph if you've created a graph that is illustrating 95% confidence intervals, because that's the nature of the 95% confidence interval, which is why I like plotting 95% confidence intervals. They're intuitive, they're inferential, they refer back to the statistical test that you're doing on the data. So that's one way of doing the Tukey's analysis. Another way that's kind of cleaner in some ways is to use Agricola. So if you don't have it loaded up already, go ahead and load it. And within Agricola, it's hsd.test, and then you put in what the analysis is. And for me, it's analysis 1. For you, it will be whatever your analysis is stored as. And then you have to tell it that the treatment is whatever the treatment is. And in this case, it goes in parentheses. I am in the console, duh. Why am I in the console? Because that's where I was hanging out a few minutes ago. So if you do that, what you should get well, that's weird. Ah, so I had to store it as an option as an object and then call up the object in order to get it to run. I'm not sure why that's the case. Yeah, that's weird. Anyway, what you get out of this is something that is the same thing in a way. It gives you the means for each of these different categories, and then it gives you this little table. And the table that it gives you basically just has letters that unite the things that are together, that are not significantly different from one another. And so what it's basically telling you, and I'm not sure why that screen is not showing you the edge. What it's basically telling you is that the 1-to-1 mixture, the 2% fructose and the 2% glucose are all not different from one another. It's telling you that sucrose is different from those, but sucrose is also different from the control, and it's telling you that the control is different from everybody else. And so you can also use these letters to signify what's different from what. And so one of the things that you could do in your figure is you could put a little A over this, or you could put AAA, B, and C, or you could put A, B, C, C, C. It doesn't really matter. But you can use letters to signify visually to your reader which things are different and which things are not. And I'll show you how to add that to your plot later. One of the difficulties with this particular plot, though, is I'm going to go up here and I'm going to change one thing about this graphic element. So I'm going to copy all of this down here. No. So this figure that I generated up here at what is in my script, line 104, this actually, I've labeled this P growth, but really it's a plot of transdat. Because my Y variable that I'm plotting is actually the transformed data here. And so I haven't really labeled this correctly. So what I'm going to do is I'm going to go down and I'm going to take this one and I'm going to convert this not using the transdat data. I'm going to use the growth data, the original data before we transformed it, because I want to make a point here. And so I also want to change my labeling to reflect the fact that I've changed what I'm actually plotting. And so I'm going to go back up here. I'm going to clear out my graphs so that I know that I'm starting anew. So I'm going to produce one graph that has the transformed data, which looks like this. And now I'm going to go and just plot the original data. Oh, I see what I did wrong. I need a new CI plot. So my original summary SE statement that I ran was running things on transdat, not on growth. So I need this whole thing. But I need it down here. And I need transdat to be growth. And then I need to make this a new thing that I'm plotting here, which is growth. So I generate a new data set, which is CI plot growth, that looks different from the CI plot that I had generated above. So you can see CI plot growth has growth as the response variable. CI plot has transdat. So if I'm going to plot growth, I needed to generate that data set. So now I've changed this to growth. That's growth. Everything is growth, growth, growth. Now I can go and generate this. Yeah, okay. So here we have two figures. In this figure, what treatment is growing fastest? The control. What one is growing next fastest? 2% sucrose, and then the three simple sugar treatments are growing the slowest. The transformed data, though, looks just the opposite, doesn't it? And the reason is that the transformation that we did on the data is we took the reciprocal of growth. That means then everything is flipped. The fastest growing things appear lowest on the figure. So you guys are looking at me quizzically, and you should, because the act of transforming the data into a form that satisfies what needs to happen for the analysis of variance to function ends up producing data that are flipped in terms of how our minds think about the data. The things with the lowest values are actually the fastest growing things. The things with the highest values are the slowest growing things. So one of the things that it might be useful to do is to back transform the data for the purposes of graphing. And so this is something that I advise all my students to do, is whenever you transform a variable, in order to make it satisfy the requirements of the method being used, you transform your data, you run your analysis. Then what you should do is you should back transform the data for producing graphs and ease of interpretation. There's nothing wrong with this figure. This figure is accurate. But in terms of easing the interpretation of the data for whoever's receiving this data, it's counterintuitive. The person has to do mental gymnastics in order to understand what's going on here. They have to constantly be flipping everything in their head. So it's useful if you, the statistician, can just make life a little easier on the receiver of the data. So how do we do this? So I'm going to clear out this, and I'm going to make this bigger so we can see things. So what we did earlier is up here, we got a summary of the data. Okay? So we ran this. But I just did you. Okay, so here we have CI plot. We created this new object. We created a new object. I called it CI plot, and it's basically just summary SE being run on the original data set on the transformed data. So one of the things I can do right here is I can just go in and get the structure of CI plot. And CI plot, as it turns out, is a data frame. And that's nice, because data frames are pretty easy to work with. So for example, I can ask R, when I look at this data frame, I can ask R, what is in the column CI plot dot transdat? And when I ask it to do that, it tells me that it has 5 elements, 1, 2, 3, 4, 5, and those 5 elements are the means of the transformed data. Now that I know that I can treat this output from summary SE just like any other data frame, I can now work with this thing to basically back transform my data. So the transformed data were transformed by basically taking the reciprocal of growth times 100. So if we want to back transform that to get growth out of these things, the formula would be Yeah, we would just divide this by Transdat, and that would give us back growth. So what we can do is we can just add things to CI plot if we want. So how do we add things to CI plot? Well, we just define a new column. So in this case, we might want to just call it the mean. And what we're going to do is use the assignment operator to basically say we're going to make a new column in the CI plot data frame. That new column will represent the average growth, and it's simply 100 divided by CI plot $transdat. And when we do that, and then we type in CI plot again, just to see what happened, we should see that now we have the control, we have the treatment, we have N, we have Transdat, we have the standard deviation, standard error, and confidence interval, and then we have a new column which is the mean, which is the back transformed data. Now remember that we had already made another CI plot called CI plot growth that should still be in the memory. And once again, we can see that the mean for growth in the control is 70, it's 69.93, so that's just going to be some mess with things in terms of doing the transformation and then doing the back transformation. But all of these means should be very close to these means. 70.1 to 69.9, 59.3, 59.3, 58.2, 58.2, 58.0, 58.1, 64.1, 64.1. So they should match up. The reason that they're not matching up perfectly is that when we did the transformation originally, we rounded to 2 decimal places. And so that's what's causing some of the wiggle in the means. Hayden, do you have a question? Oh yeah, I didn't give you guys your sticky pads, your sticky notes today. All right, so let's see. Show me what CI plot looks like in yours. Just run the next line. Okay. So when you run that, what error do you get? Oh, that's weird.
I was getting this error.
That's weird. Okay, so now call up CI plot again.
Oh.
Oop, go back. Yeah, there it is. Okay. Everybody else with me? Okay, so what's the next thing that we need to do? Is we need the lower limit and the upper limit of the confidence interval. So we can go in and we can add a new column, CI plot, $, lower limit. We'll just start with lower limit, I guess. And once again, that is simply the one way to do it would be to do 100 divided by CI plot Transdat, which is the mean minus CI plot CI. So the lower limit is the mean minus the confidence interval. That then represents a value in the transformed data, and then to back transform that value, we divide that into 100. And so when we do that, that should once again give us a new column because we're doing new things. It's always nice to check and see that it did what we thought it would do. Ah, but since we're working on the reciprocal, when we subtract the confidence interval, that actually gives us the upper limit. So let's go back and rewrite that so that this is the upper limit. So the upper limit of the confidence interval should be higher than the mean. The lower limit should be lower than the mean, but because we're working with the reciprocals of everything, now we need to take this thing here, copy it, paste it here. This will now be the lower limit, and this will be the confidence interval added to it. So now we have a new CI plot with the mean, the lower limit, and the upper limit. Mean, lower limit, upper limit, mean, lower limit, upper limit, mean, lower limit, upper, mean, lower, upper. The fact that I made the mistake of thinking that I needed to subtract the confidence interval to get the lower limit indicates once again why we would want to be doing this anyway, because it's counterintuitive because of the type of transformation that we had to make. Now remember that when we define error bars in a graphing block, we usually just take the y-min and add and subtract the confidence interval to it. But because we transformed the data, one of the reasons that we transformed the data is that the data were slightly skewed. And as a result of that, the confidence intervals might also be slightly skewed. So we have to what am I trying to think of? Conserve that skew when we make our confidence intervals. So for our distance above the mean and distance below the mean, those may be two differences because of the transformation that we did. So what we need to do now is look at what the difference is between the mean and the upper limit and the mean of the lower limit. And so we're going to add a couple more columns to our CI plot. So let's call this thing CI plot $ upper range. And we're going to use the assignment operator. And to get the range, we're just basically going to take CI plot $ upper limit and subtract from that CI plot mean. And I did something wrong somewhere. Oh. Now, when I do CI plot again, actually, let me straighten up my code a little bit here. So when I run that, I can look at CI plot again, CI plot. And now I have an upper range. And then I can do the same thing. So I'm just going to copy and paste again. And in this case, I want to take CI plot and I want to subtract the lower limit now. So I want to take the mean minus the CI plot $ lower limit. Oh, crud. I didn't change upper range to lower range. All right, so I need to redo upper range, and I need to make this lower range. So now we have the mean, the lower limit, and the upper limit. But when we look at the actual distance between the mean and the upper limit, it's actually 2.89. When we look at the difference between the mean and the lower limit, it's actually 2.67. So these confidence intervals are slightly skewed. The upper limit is higher than the lower limit is below it. The upper limit is more above the mean than the lower limit is below the mean because of the transformation that we ran. Similar thing here. Going to the upper limit is slightly higher than going down to the lower limit. Going from the upper limit to the lower limit, those are different distances. There are slightly different distances, but they are different. If the data had been really skewed, those differences would be even more pronounced. So now, what we have is we have a CI plot data frame here that contains all the information for the transformed data, and it also has all the information we need for the back transformed data. So now that we have that, I'm going to go down here to the very bottom. I'm going to get this graphing block, and I'm just going to make a copy of it so that I don't mess up my work before. And I'm going to make myself a note. A graph of the back transformed data. And so what we're going to be doing is we're going to be still using CI plots. We're not going to be using CI plot. And we're not going to be using growth. We're actually going to still be using treatment. But y in this case is going to be the mean. Y min is going to be the mean minus the lower range. And the max is going to be the mean plus the upper range. So in this case, before we could just say add and subtract the confidence interval, but in this case, the confidence interval above the mean is different from the confidence interval below the mean, so we actually have to have two columns for those two values. When we look at the rest of our graphing block, everything else stays the same. So in theory, let's go and run the untransformed data. So I'm going to start adding some other things to my. So this is a new graphing block. Let's be more descriptive with that. This is a graphing block for the raw data, untransformed. This is why annotating your script becomes helpful. Then we have a graphing block for back transformed data. So I'm going to name this figure a different name. P growth back, P growth back, to separate it from P growth, which also separates it from P transdat. So now I have three different figures. P transdat, P growth, and P growth back. So let's run all three of these. Let's run P transdat. That gives us a figure. Let's run P growth. That gives us a figure. And let's run P growth back. No, something happened. Oh, growth. This should all be mean. So you get an error message that says it doesn't recognize growth, and you're like, I already changed growth right here, but I didn't change it for all of these as well. So now let's run that again, and we get that. So what we have now is we have three different graphs. The first graph is the transformed data. And it looks flipped. Everything looks flipped. Things that are growing fast look like they're growing slow. Things that are growing slow look like they're growing fast. The next graph is just the raw data. But when you look at it, if you look at it carefully, these error bars are symmetrical, even though the data that underlie them are not symmetrical. But because of the way you form the confidence intervals, they end up being symmetrical. And the last graph, even though it's very subtle, well, maybe I didn't have, did I generate all of them? Why do I only have two graphs? P-transdat, generated. P-gross generated. And P-growth back. Okay, so that's all three. So we have the transformed data, we have the raw data. You see that in the raw data, the mean is just a touch above 70. And then in the back transformed data, it's very subtle. Raw data, back transformed data. But what you saw, I don't know if you could see it, is this error bar popped up a little bit and this error bar popped up a little bit. And the mean just changed ever so slightly. Once again, in this data set, it's not making that big of a difference, but I've had data sets in the past where the confidence intervals for the back transformed data were really skewed because the original data looked like this. And rather than a reciprocal transformation, what we did was we did a logarithmic transformation. What a logarithmic transformation does is these low value observations don't change much at all, and these high value items come really far in. And so, depending on the type of transformation that you do, it's going to make a big difference in how your graph appears. But the advantage of back transforming is that now when somebody looks at this figure, they're like, oh, these people were studying growth. Well, who grew faster? The control grew faster. Who grew slowest? These guys grew slowest. So even though it's a little pain in the butt to do, it's always a good idea to go back and back transform your data for production of what people will ultimately be doing, which is interpreting what they see visually in your graphs. All right. That seemed like a lot. Yeah, Chance.
I accidentally renamed a column on it.
Oh, huh.
I did upper range and spelled it wrong, so I reran it, but now I have two upper ranges. How do I get rid of the other one? Sorry. See, I've got upper range. How do I rid
Okay.
of this column?
So there is a way to delete a column, and I can't remember right off the top of my head. But one of the things that you can do, where are you at in all of this?
It's right there.
Where did you generate summary SE? Is this summary SE? Yeah, this is. Regenerate that. Now look at it. Those things are all gone. Now go back down and just regenerate it. That's the sloppy, inelegant way of doing it. There is a more elegant way of getting rid of a column. I just can't think of what it is. Questions about what we did today? My apologies, as I was live coding, I was making mistakes as I went, and I was going back and fixing those. Hopefully you were able to follow along pretty well what was going on. And everybody has back transformed their data, correct? And it all looks like mine does. Okay. Yeah. All right. Let me see your file. So let me see CI plot. Okay, so where are that's on growth then. Where's your transformed data? So go up to the start of all of this. Ah, okay. So you keep naming things CI plot. So every time, so what you've done, when you got down here, you made all these changes. And then when you got down here, you regenerated a new CI plot that is based on growth. So you've overwritten what you did before. So you need to go back up to that. And you see that on mine, what I have is my original running of summary SE on the transformed data. Right now, if I run CI plot, it has all these things in it. It has the lower range, the upper range, all that stuff. But if I just go back and run this line again, all that, whoa. Okay, it's saving it, and now it's not letting me override it. But what I've done is I've saved one with the tag CI plot. The other one I saved with the tag CI plot growth. So if I was to go back and run this now, when I go and get CI plot, it just has the growth data. It doesn't have the transformed data. So then I would have to go back up here, regenerate the transformed data in a CI plot. Why is it giving me that error? Why is there an error in my data frame? Yeah, this is why we should name things different things. That's weird. Oh. Haha. Somewhere along the line, I didn't transform my data. That was my problem. So let's go back and make this CI plot. If I do this, it'll give me the transformed data. And so if I want to hold on to all of that, but I lost all my calculations, so I have to go back and rerun all of this to recreate that data file. So now, if I want to make another data frame for graphing the regular growth data, I can't just name it CI plot again. I have to give it a different name. Otherwise, it'll overwrite what I just did a few minutes ago. Now this is growth as opposed to transdat. Okay, so that's all you did. You overwrote your data frame with your transformed data in it. Does that make sense? Does it do it now?
I changed this one to CI plot growth.
Uh-huh.
And then I can leave this one, right?
Yeah, you can just leave that one alone. But you have to go back and regenerate all that now because you overwrote it earlier. Yeah, see, it's repopulating. Yeah, there you go. Yep. Nope, you just overrode it again.
I didn't want to use it down here. I thought I wanted to use this down here.
What did you name? See that CI plot, but go down. Then you get here CI plot. That's growth. So you've just overwritten everything that you did up there. So you need to change this one. CI plot 2 works also. Now you have to go and regenerate all that. Yeah. Okay, so now you have two CI plots. You'll use one to plot the transformed data. You'll use the other one to plot the back. You'll use one to plot the transformed data and the back transformed data. You'll use the other one to plot raw data. But really and truly, you shouldn't have all three of those in a report. You should only have the back transformed data in the report. I generated those three to show you how they vary and how, in particular, one is counterintuitive, and you shouldn't present that to somebody because it's just going to confuse them in the end. Okay? Right, I feel like I loaded a lot on you today, so I think we're out of time anyway. Um, on Monday, what we will do is we will talk about contrast and how to run contrast. I was hoping we would get to that today, but we didn't. So that's what we'll work on Monday. And today I'm going to send out the problem set for ANOVAs. I have some ANOVAs that you can work by hand. And if I were you, I would also get in the habit of plunking them into R and working them through R so that you can, once again, just get practice coding scripting in R as you do it. But what I'm going to expect out of you is basically either hand calculations or Excel sheets. And I will send you some guidance on Moodle that tells you if you're going to do it in an Excel sheet, this is the way that you can structure it that makes it easier for me. I put each question in its own worksheet within a workbook, and then I make sure that I label everything really carefully so that I can see what I've done. So you should also do that for me so that I can see what you've done. And then the other thing that I'll do in my script, in my Excel sheets, I'll also color code things so that the calculations for mean squared error may be in blue. The calculations for mean squared treatment are in red, et cetera, et cetera. And that color coding is both in the calculations up above and it's also in the ANOVA table. I'll send you an example of what mine looks like for the P's analysis so you kind of get an idea of how you can do that. If you do that, it just makes it quicker and easier for me to grade it rather than if I'm having to hunt around in this sea of figures looking for where your answers are to different things. So I'll send that out later on today. Thanks for coming, and I will see you guys next time. Save your script if you haven't already. Hayden, how was today? Okay. Feeling a little more confident? All right.